Have you ever stopped to think about how we went from, say, guessing the size of a field to calculating the exact path of a spacecraft billions of miles away? Well, it all comes down to one of the most basic and maybe most important ideas in all of science: measurement. See, before we can even begin to understand the universe, we have to agree on how to describe it.
I mean, that is a huge question, right? And to even get started, we need a common language, a kind of universal translator for reality itself. Just think about it for a second. If we didn't have a shared system for what a kilogram is or what a second means, science would be total chaos. You couldn't build a bridge, let alone a rocket.
So let's dive into that language. We're about to see that measurement isn't just some boring chore from high school physics class. No, it's the absolute bedrock, the foundation that everything else is built on. So what is measurement, really? Well, at its core, it's just a comparison. When you say a table is 2 meters long, what you're really saying is that it's twice the length of this thing we've all agreed to call a meter. You've got the number, 2, and the unit meter. And you need both. You can't just say 2. 2 what? 2 inches? 2 light years? The unit is what gives the number its entire meaning. Now, to make sure scientists all over the world weren't just talking past each other, we all agreed on one standard system, the SI, or the International System of Units. And here they are, the 7 fundamental building blocks of reality. Think of them like the ultimate Lego bricks, seriously. Every other physical thing you can possibly measure, speed, energy, pressure, you name it, is just some combination of these 7 basic units. Okay, so now that we have a language to describe things, let's tackle a much older, much deeper question. It's a question that puzzled the greatest minds for centuries. What makes things move? And maybe even more importantly, what makes them stop? For more than 2,000 years, this idea from the ancient Greek philosopher Aristotle was pretty much the final word. He argued that the natural state of anything is just to be at rest, to not be moving. So if something is moving, well, something else has to be actively pushing or pulling it. And you know what? To be fair to Aristotle, this makes perfect sense based on everything we see around us every single day. If you stop pedaling your bike, you slow down and stop. If you slide a book across a table, it comes to a halt. Our everyday experience seems to shout that Aristotle had it right. If you leave things alone, they just stop. But here's the big twist. That common sense view is completely, fundamentally wrong. Aristotle, for all his genius, missed a huge piece of the puzzle. So what was it? What was this invisible thing that was happening right in front of his eyes?
The answer finally came along in the 17th century, thanks to a guy named Galileo Galilei. Now, he didn't just sit in an armchair and think about it, he actually did experiments. And what he figured out, using just some simple ramps and balls, would completely overturn 2,000 years of scientific dogma.
Galileo's logic was just beautiful in its simplicity. He noticed that, obviously, a ball speeds up when it rolls downhill, and it slows down when it rolls uphill. So he asked the brilliant question, what happens in between? What happens on a perfectly flat surface? He reasoned that if there's nothing to speed it up and nothing to slow it down, then it should do neither. It should just keep going, forever. And that was it. That was the invisible culprit Aristotle missed. Friction. The book stops because the table is pushing back on it. The bike stops because of air resistance and friction in the gears. The natural state isn't rest at all. It's just that here on Earth, these opposing forces like friction are always there. Galileo's genius was being able to imagine a perfect world without them. So let's put these two ideas side by side, because this is a huge shift in thinking. Aristotle thought you needed a constant force to keep something moving, but Galileo realized, no, you only need a force to change its motion, to speed it up, slow it down, or change its direction. From this new perspective, just sitting still and moving at a constant speed are basically the same thing. They're both what happens when there's zero net force acting on you. And this fundamental property that Galileo discovered is what we call inertia. Now, it's not a force, it's just an object's built-in laziness, its resistance to change. An object at rest wants to stay at rest. An object in motion wants to stay in motion. It's that simple. So Galileo kicked the door open, but it was Isaac Newton who walked through and basically built the entire house of classical mechanics. He took Galileo's ideas and sharpened them into 3 incredibly elegant and universal laws that govern how everything moves, from an apple falling from a tree to planets orbiting the sun. Okay, Newton's first law is pretty much just a formal, fancy way of saying what Galileo figured out about inertia.
In plain English, things just keep doing what they're already doing. If all the forces on an object cancel each other out, it's not going to accelerate. It'll either stay put or it'll keep cruising in a straight line at a constant speed, kind of like a spaceship just gliding through empty space. The first law tells us what happens when there's no net force. But what about when there is one? Well, to answer that, Newton came up with a new idea: momentum. You can think of it as how much motion an object has. It's a combination of its mass and its velocity. This is exactly why a big, slow-moving truck can be just as hard to stop as a tiny, super-fast bullet. They can have the same amount of momentum.
And that brings us to what might be the most famous equation in all of physics, Newton's second law. It's beautifully simple. It just connects force, mass, and acceleration. If you apply a force to an object, it accelerates. The more force you apply, the more it accelerates. And the more mass it has, the less it accelerates. It's the powerful, simple rule that tells you exactly how things change their motion.
Newton's third and final law is probably the one you've heard before. It says that forces never exist on their own. They always come in pairs. When you push on a wall, the wall pushes back on you with a force that's equal in strength but opposite in direction. Now, the key thing to remember is that these two forces act on different things. One's on the wall, one's on you, so they don't just cancel each other out. Now, I know these laws might seem a bit abstract, a bit academic, but the truth is they're the literal operating manual for our physical world. Their applications are absolutely everywhere, in pretty much every piece of technology we use and everything we do. Just look around you. The crumple zones in a car, they're designed using the second law to make a crash last longer, which reduces the force on you. A rocket taking off is a perfect display of the third law. The rocket pushes hot gas down, that's the action, and the gas pushes the rocket up, that's the reaction. These aren't just old ideas from a textbook. They are the living, breathing principles that make our entire modern world possible. And that brings us right back to where we started. From the simple act of all agreeing on what a meter is, we've journeyed through ancient mistakes to Galileo's brilliant insights and finally to Newton's universal laws. It just goes to show you, once we figured out the language to describe the world, we finally unlocked the ability to understand its rules. Which makes you wonder, what new rules are we just starting to learn how to measure today?